Top of the hour. So we'll get started here. So hello, everybody. As everyone is joining, my name is Julia Petrie, and I'd like to thank you for tuning in to our very first SDEC session of 2023. So today we do have Jamarius Taylor, data scientist at Search Discovery, here to walk you through untangling the confusion matrix in this interactive lab format. He holds a business analytics degree from Auburn University and currently leads the Search Discovery data science community. He is passionate about all things analytics and R and has experience in the wide range of BI tools, cloud products, and tag management systems to bring you an expert point of view. So sit back, relax, and place your questions in the Q&A feature, and we will get to those at the end. So with that, I'll turn it over to Jamarius to take it away.
All right, thank you. What an introduction. So yeah, I'm Jamarius Taylor, data scientist here at Search Discovery, and we're going to talk about the confusion matrix. For those of you that are data scientists, this should be, or in that realm, this should be a fun, another way of talking about and communicating this. And for those of you that aren't, this should be a very fun, low math. I didn't say no math, but it should be a very fun, low math introduction to something that data scientists kind of deal with all the time. And I think that the major takeaway that I want to get is that everybody is going to be able to speak the same language at the end of this. If that's the case, then you don't remember any math, and that's also good. I'm still going to count that as a success. So let's dig in and get started, why don't we? All right, so first things first. I'm going to say this, there's probably more, but they're mostly 4 data science problems, and they're represented here. So what we're going to focus on today is the classification problems. So we're not going to talk about any specific models or anything, because the cool thing about what we're going to learn today is that no matter what model you choose to use, whether you choose to use a neural network or something, or XGBoost, or you're just using regular logistic regression, you're still going to need to understand what we're talking about today. And that's going to be a great help going forward. So we're doing classification problems, which means that our problem is going to be discrete and supervised. It's going to be discrete, meaning that whatever the variable that we're looking for as an outcome can only take one specific value instead of like an interval. And then finally, we're also talking about supervised problems, which means that our data set is going to be labeled, or else we're going to have answers previously, and then we're going to be able to fit this to information where we might not have the answer to. So basically what I'm trying to say is that in problem framing, we're talking about heads or tails questions. We're talking about conversions or no conversions. We're talking about making or missing shots and things like that. You can do classification with more than just binary problems, but for the sake of this webinar, we're only going to talk binary problems. So what is the confusion matrix? Well, it's called that because the more you look at it, the more confused you'll become. So let's build our own confusion matrix, right? So first and foremost, we're talking about classification problems, binary outputs, and then we're also talking about what we observed versus what we're guessing or what we're expecting, what we're predicting maybe. So when we're building it, the first things first is that we're going to have our observed values. You can think of this as the truth, what actually happened. Any of those words are fine. Just know that that's what is on top in most visuals, or you'll also see it called observed. So let's use a heads or tails example, or just any binary example. We only have 2 positive outcomes because it's binary. We have heads, we have tails, we have true, we have false. You can flip this around too to have tails be true and heads be false, but for our example, we're going to have heads be true and tails be false, which means we're trying to build a machine that can tell us when heads is going to come up on the coin, or when something's going to be true. So we're building a true machine essentially. Next, we have our predicted outcomes. And so this is what we expect. This is what we predict. This is what the models are returning. And so you would imagine that because this is a binary classification problem, and we see that true and false is up top, or heads and tails, that's what we're going to get here. True, false, heads, tails. And so right now, it's not quite confusing yet, but we do have a matrix. And so you can see that's why it's called a confusion matrix, because there's the matrix part. Now let's get into a bit of the confusing part, shall we? Okay, so first things first, let's start filling in this the center of this matrix here. So the first thing we have is we expected it to be true and it was observed as true, or what we call a true positive. Next, we'll have the opposite of that. So when we think it's false and it is false, we have a true negative here. Now, this is where it starts to get a little dicey. If we predict that it's false, but it was actually true, then what we have here is a false negative, right? And it makes sense because of kind of what we're looking at here. It was negative and we predicted false. You'll also hear this called a type 1 error. Now, this is where it gets mostly confusing, is because statisticians, data scientists, numbers folks, people of that ilk love to throw around type 1 error, type 2 error, and talking about things like that. And it gets kind of confusing, but the secret is that it also gets confusing for us on the data science side as well. Because somebody, especially early in the morning before I've had, time to wake up, it's like, yeah, we have this problem. There's all this type 1 error. I'll be honest with you, I've asked, okay, which one is that one again? So if you hear this type 1 error and you're not familiar with what's going on, feel free to stop and say, hey, which one is that one again? What are we working with here? So just like there's a true positive and a true negative, there's a type 1 error or a false negative, we can also have false positives. False positives will be the opposite of the false negatives. And so by that logic, we can imagine that you can also call a false positive a type 2 error. And so type 2 error is your false positives. You can also think of it as upper right-hand box, lower left-hand of the box. Whichever one kind of helps you. Another thing that helps me is that they both are going to have false in the title, so that's not going to be helpful. But N does come before P in the alphabet, so I like to call false negatives type 1s. I like to do it in alphabetical order. It kind of helps a little bit there as well, but the best help is just asking. So let's do a story time here and let's try to set up our own confusion matrix, right? So bear with me here as we build this story out. So like imagine you're walking from your house to a friend's house, and this is what the street path kind of looks like. We've seen cities before, neighborhoods where you have to kind of go down and over. But we do know that the quickest way from point A to B is a straight line. So the teal line is actually our optimal path. And we're going to assume that there's no property or anything in the middle of this, that you could make this walk if you wanted to. Let's throw a wrench in the plan. So in the middle of the path now, there's a deadly obstruction. We're going to say it's a snake, but the snake's not always there. So now you have an option here, right? You can decide to take the long way, or you can decide to take the short way and gamble if the snake is going to be there or not. And hopefully, for those of you that are in this presentation, when I say, is the snake going to be there or not, it kind of triggers the alarm bells that tells you, oh, this is a classification problem. So let's find our optimal choice for the shortest trip. And let's set up our confusion matrix for this classification problem. So we can observe two things. The snake is not there or the snake is there. We're also assuming this snake is, like I said, it's deadly and very fatal. So then if that's what we've observed from the snake, that it's there, it's not there, then we can, when we're leaving our house, we have to make a decision. Is the snake not there or is the snake there? So what we're looking to build here is a machine that tells us when the snake isn't there. So now let's take a look at how long it takes us to get place to place. So if you remember the diagram, when the snake is not there, then we would take the shortest path, which means it would take us about 5 minutes. If the snake is there and we think it's there, then we have to take the long way. So we have to go down and over, which is going to take us 10 minutes. It's going to double our time. So this is what happens with our true positive and true negative cases. So now if we believe the snake is there, but the snake is not there, then it's going to take us 10 minutes, but there's no snake to even consider to deal with there. And then finally, If the snake is there, if we think the snake is not there and the snake is there, then it's fatal and we're going to die. So looking at this confusion matrix that we've set up here, it's kind of let us know immediately that oftentimes what we think about in classification problems is how many times were we right and how many times were we wrong. But that's not always the case. It's not always the case in marketing. It's not always the case in this snake example. It's not always the case in life, where sometimes we can afford to be a little wrong or a little right, and sometimes we can't. And in this case, we can't afford to be wrong because the snake's not there then, or if the snake is there, we don't think it's there, then that's the end of us, and it doesn't really matter how long it's going to take us to get there because we're never getting there. And so it's important, I think, when trying to frame these problems of, will somebody convert? Will somebody make this shot? Yes, we do want to know what's their likelihood of making it, what's the probability and things like that. But also, let's take a step further and think, what are the consequences of if they make it? What are the consequences of us being wrong? And so this just tells us here that we can't afford one error, but we can afford another error. So sometimes you have to decide, is it okay to have a type 1 error or a type 2 error? That's pretty much what I was saying. So let's do another example here, one that is a little less gruesome. So let's have the same house set up, but instead of there being a snake on the short path, on the long path, there's a man who gives out free ice cream. There's just free ice cream in the neighborhood, and we have a huge sweet tooth in this example. So let's set it up again. There's an ice cream man, there is no ice cream man. Those are our two options, right? So hopefully, and I know it probably sounds repetitive, but I'm going to beat this into everybody. Let's see what our expected examples are. Surprise, they're the exact same as our observed examples, and they always will be. So let's just fill in our blanks here. So if there is an ice cream man, then I'm going to take the long way to my friend's house. It takes me 10 minutes, but I get ice cream. Woohoo. If there is no ice cream man, and I think there's no ice cream man, then I'm going to take 5 minutes, but I'm not going to get any ice cream. But that's okay, because there's no ice cream to be had. These are all the positive examples, or the true examples. So let's look at the false examples. Down here, if there is no ice cream man, if I think there's no ice cream man, but there was one, then I do get to my friend's house earlier, but I missed out on ice cream. And like I said earlier, I have a huge sweet tooth, and that's upsetting. So here now, if I believe that there is an ice cream man and there is no ice cream man, I might have taken longer to get to my friend's house, but I know I didn't miss out on ice cream, and so the FOMO isn't going to kill me. So now looking at this, we can see our focus shifts from the type 2 errors that were untenable, right, because we were going to die to the snake, now to the type 1 errors that are untenable because we cannot afford to miss out on free ice cream in this economy. And so it's important, again, to be able to set these up and not just set them up and start doing the math and looking at the numbers. You'll notice I haven't introduced any of the math actually to this section because I want to talk about how important it is to make the correct decisions based off of what you're doing, and not just because like you've built a model that's really good at one thing. Because if it's really good at one thing and it's not actually serving you, then it's actually a hindrance, and we don't want to be a hindrance. Okay, so I just showed you a bunch of kind of outcomes and things, and I keep saying like we can optimize towards, we can make our metrics go towards this. Well, let's talk about what those metrics are and what they look like. So there are several metrics that we can use to evaluate classification models. Those metrics are accuracy and precision, recall, sensitivity, specificity, and the F1 score. We're going to go over each one of those examples here and how to calculate them and kind of when to use which one. So the first one is accuracy. This is the one that everybody is most familiar with likely. It's just how many times did you get it right over how many observations were there total, so how many at bats. And this is pretty easy when you have like a more symmetrical data set. So especially if you're playing a zero-sum game, then you can use accuracy because somebody has to win, somebody has to lose. And each use case is as likely to happen as the other one, even though this data here isn't super symmetrical. Precision, on the other hand, is for when we want to be more confident of our true positive values. We can't afford the type 2 errors here, right? We want to predict true or a 0 or a win, whatever it is. We want to predict that, and we want to be correct about it. We want to minimize our false positives. So for instance, if we say the snake is not going to be there, then we better be damn sure that the snake isn't there. because if it is there, it's going to kill us. So you can think of it as kind of in that zone, but also here's the formula for precision, and it's just your true positives divided by your true positives plus your false positives. So you'll see oftentimes for most of these formulas, the formula that we're looking at will only span across one row or one column. So then when you go back to the very beginning of this and you build out your confusion matrix with no numbers and you just talk about what are the outcomes, you can then find the two outcomes, whether they be in a row or a column together, that you are seeking to work with. And then you can go back and reference these to figure out which metrics will go with the scenario that you have set up. Next, let's look at recall and sensitivity. So you'll notice that these slides are the exact same, and that's because sensitivity and recall are actually the exact same. One is just paired with a different metric. Why is that the case? I do not know, but alas, here we are. So here we go with the sensitivity. If the idea of false positives is better than like a false negative, then we can go with that, right? So for this, we don't want to miss the free ice cream. So we're okay with saying that the ice cream man's going to be there and he's not there. And that's okay, because the worst thing is that we lose 5 extra minutes, but we make sure that if there was ice cream to be had, then we had the ice cream, and we want to make sure that we, get all the ice cream that's on the table, proverbially. So for this one, it looks like this. Recall and sensitivity, it looks like this. You have true positive over your true positive plus your false negative, or like I said earlier, it just works in this column. So then when we take a look and we see that the ice cream is down here, and this is what we're trying to minimize, then we can go back and find that recall or sensitivity is going to be the best case metric for us here. Let's talk about specificity now. So this one's a little trickier, but it also just allows us to avoid some false alarms here. We don't want false positives, and we want to cover all of our true negatives. This will allow us to avoid the snake first and foremost. I have another example here about PagerDuty that I'll let you read on your own time because you'll get these slides. But if the snake and everything is getting a little confusing, then here's a separate example for you. So if we look at specificity, we see here once again, this is the top right-hand corner is where the snake would have been. And so that tells us that this is the column that we're working with. So we could come back and find that we want to talk specificity. And so when you are the business person and you can say like, oh yeah, we're talking specificity because I'm trying to avoid this specific outcome, or like we need less of these, it'll help kind of whoever you're working with on the data science side. And then vice versa, if you know that somebody is looking for this, then you can kind of break down like, okay, I think these are your 4 outcomes and this is the best metric for it. So it goes both ways. Finally, we have F1 score. F1 score is for when you need to deal with both precision and recall evenly. So these two have a trade-off, and as with most things in life and data science, there's always a trade-off, bias and variance. Today's trade-off is precision and recall. This allows us to keep both of them in check. It works really well when you have that imbalanced data set, so more zeros than ones, more trues than falses, more makes than misses, so forth and so on. It allows you to keep both of them in check. And then for the data scientists playing along at home, this is what's called the harmonic mean, which just means it keeps both of them in check. And so that's our F1 score. All right. So now we're going to do a follow along example, and I believe Julia's going to help me out. But basically, I'm just going to poll the crowd here for some like classification, some binary classification problems, and we're going to pick a couple and then set up our own confusion matrix to go along with it.
All right, and if you have any ideas for the example, please feel free to put those in the chat.
And how are we doing on time, Julia?
Yes, we're doing just fine.
Good.
All right, well, if we want to, we could do the golf example.
Okay. let's do some examples then. And we're actually going to, oh, sorry, I'm actually a little ahead of my skis here. Let's do this first example, and then let's get into the golf and everything else. So this is an example that I actually ran through during the dress rehearsal for this. So I actually ran through this example with Julia. And essentially what happened was we grabbed a coin digitally and a piece of paper, Google Sheets. For those of you that don't know, you can type in sheets.new and it'll give you a Google Sheet, like a blank Google Sheet for you. So what you're going to want to do is you're going to want to set up two columns, one called predicted and one called observed, just like I have here. And then you're going to want to make your predictions, and then you're going to want to flip the coin. So you'll just bounce back and forth. So essentially, I asked Julia what she thought the coin would land on. She would tell me, and that's what was predicted. And then we'd go to our observed, and we would see what would happen there. And so do that about 10 times. You can do it more than 10 times. Like I said, you'll also get the slides, so you'll be able to kind of follow along if you're trying to bring this back to somebody or you're trying to explain this. Then this example will work for you there as well. But do that, and for the sake of brevity, we've already done it, and here are the results. So you can see Julia has a few right answers, a few wrong answers, so we should have a good mix. So, oops, that is not right. There we go. Sheets are out of sync. So here we go. So this is how it worked out for Julia. Like I said, up top we have the observed, and on the left-hand side we have the predicted. So she got a total of 5 correct, which is good for an accuracy score of 50%. So how we calculate this? We would do 2 and 3 is 5, and then another 2 and 3 is 5. So 5 and 5 is 10. And then we take how many she got correct. So the heads, tails, tails, or the true positives and true negatives. And that just gives us an accuracy score of 50%. Next, we can calculate her precision by taking the true positives, so everything in the top left-hand corner, and then the false positives, everything in the bottom left-hand corner. And here I am actually messing this up, top right-hand corner. And we can do it again. And so this will also come out to our 50% because we'll have 2 divided by 4. We can calculate the recall here by doing, once again, the same thing, going out and finding what we're looking for. So our true positive and then our false negative. And then we'll do 2 over 5, which will come out to about 40%. And then finally our F1 score, which I will not be calculating because I'm not doing that level of mental math on the recording. But you could definitely figure it out from here when you go through the example. And so that's pretty much how simple it is to be able to kind of set up and diagnose and talk through your confusion matrix. How did I get sensitivity out of order? Sensitivity, once again, is scored here. The formula is here, and you can go through it. And then there's specificity. Now we're going to go through examples where we frame our own problems. So here is kind of a PDF that you'll get, or it's a slide now, but you'll get this in PDF form after the call, and you'll be able to kind of go through and set these up and work with your stakeholders or whoever it is, and work with everyone kind of working in this framework of like, let's talk about what it is that we're doing and what it is that the outcomes are and what do we want to try to use to create a better model in our confusion matrix. Previously we had done an example in the dress rehearsal talking about golf. So for those of you that do not golf, I apologize. I'll try to make this quick and painless. For those of you that do golf, you're in for a treat. So in golf, there's oftentimes just like in most sports, there's a time to kind of go for it, and there's a time to play it safe. So then what we know now is that for our expected values, we can go for it or we can play it safe. So then what we'll do here now is we'll have to talk about, okay, what happens with the outcomes. So now we're seeing the expected values, and expected or predicted makes it sound kind of weird. So we'll actually, one, we'll put golf here, but two, it's already justified. Two, we'll also, instead of calling this expected or predicted, we'll say that, or observed, we'll say like best play. Oops. We'll put best play, and then we'll put actual play. So now that we've set this confusion matrix up to look like this, everything that's happening on the left is still in play, but we've now set it up for a specific example of what's going on. So when we go for it and we should have gone for it, then we can safely say that like, okay, cool, we would have birdied that hole. So -1. And of course, if you're not familiar with golf, low score wins. So -1 is pretty good. If we decide to play it safe, and that was the correct play, then that's all right. We'll just par the hole. And a 0 is still good to put on the scorecard. So those are our true outcomes, right? True positive, true negative. And so that's fine. Next, let's see what happens when we should have went for it, but we played it safe, and we'll bogey that hole. So we could have done better, but we didn't. A 1 on the scorecard is not bad. If you've ever seen me play golf, you know that I'm begging to play bogey golf. And finally, if I go for it and I shouldn't have gone for it, then we'll call that a double bogey. So now we can take a look at what we have here, and we just find out what it is that we are trying to keep together. And so for some people, their biggest concern is going to be trying to eliminate this false positive here, right? And so if you're trying to eliminate your false positives and you want more true positives, then you can go with something like precision. Precision is what works on across these columns here. And it's going to help you get less, basically less double bogeys and then more birdies. And that's pretty much what we all want. And so now we've gone through and we set it up. We haven't actually had to use any real numbers yet. If we're talking, again, to our engineers, to our data scientists, to our analysts, whoever we're talking to, we can say, hey, I've set this up. This is what we're looking at. This is what I want to work with. And then from there, they can go, okay, cool. We have the data, and now we know that this is a precision problem. And we can kind of go through it. We have 3 minutes, Julie. Do we have time for another one, or should we cut to questions early? What do you think?
Yeah, we could give another example, maybe this one more business focused.
Okay, let's do it. So let's talk about, and I'm going to let's talk about GDPR and CCPA, because I think those are two things that a lot of folks on this call, I cannot center anything today, have some problems with, or at least are experiencing a lot of. So with GDPR and CCPA, for those of you that don't know, every time you see a cookie banner pop up at the bottom that says, hey, we're collecting data, we're tracking data, please opt in or opt out. This is kind of the main culprit is GDPR, which came online in about 2018. And CCPA, which I'm not 100% sure when that came about, but is definitely influencing a lot of what we do today on the internet. And so if you have any more questions about that, shameless plug to check out Corey Underwood, because that's where I get all of my information. So let's get back to the confusion matrix. So now you're probably asking yourself, okay, we need to set up our like tracking here. So then what are our options? So the options are the person opts in or the person opts out, which means that, of course, this person could opt in or this person could opt out down here. Now, as we're looking at this, we'll have to frame this again because expected and observed don't quite work out, but it's going to say user selection, and then we'll call this site action. So site action is in, are we going to collect data? Are we not going to collect data? User selection, have they opted in? Have they opted out? So how are you going to treat them? So first and foremost, they opt in and you treat them as they opted in, then we collect data, right? That's great. We're a data, well, here at Search Discovery, we're a data business. That's what we want to do. And you guys are data people, so that's good. If they opt out, then then we do not collect any data. Ooh, sad, right? But now let's talk about what happens with our false classes here. So if a user has opted in and we treat them like they opted out, then we don't collect data. If a user has opted out, but we treat them like they opted in, then we could end up being sued big time. And what this means here, because these two are the same, is that this is no data, but we're not sued, just for more context. And this is no data for no reason. So now we take a look at this and we see what we have to work with here. So I think that we can all agree immediately that the first thing we see when we look at this chart is that the word sued is on it. And when you go through legal, that's the first thing that they're going to see. So this is going to kind of turn out to not be super fun because it's just going to come to be the same precision score because we want to get rid of the false positives here because we cannot end up being sued. The fines for GDPR in Europe and CCPA in California are kind of large and would definitely not be something that we're looking for. So we can quickly kind of diagnose this one. Oh, that's good. We can quickly kind of diagnose this one and say, all right, that is exactly what we're trying to avoid. And that's what we're going to use as precision. And then you can send this off to engineering and say, all right, let's make it so that we don't get sued. Here are the kind of the outcomes. All right. And so, yeah, and you'll see a lot of this also just for homework, I guess. You'll see a lot of like talk like this in like decision sciences and like game theory, and they'll focus less on the math, kind of how I have today, and mostly on the outcomes and what that looks like. And I think it's very neat that exists because it's not always about like what numbers can we get out of this and how good can we make it, but really what is the outcome of what we're seeing here. And I will leave these examples in the slides so when they come out with the recording, everything matches up, but you'll also get blank versions of these slides. All right. So like I said, I'm Jamarius Taylor, data scientist here at Search Discovery. You can email me at jamariussearchdiscovery.com. You can have a link to my GitHub. I also write things on my own personal site and on LinkedIn and for Search Discovery. So if you like, just kind of like Google it, you'll see all of my random musings and things out there. But hopefully this has been a help to some of you, and I think we are ready for questions.
Awesome. Well, thank you so much, Jamarius. And while we have you here, we'll open it up for those questions. So if you would like to put those in the Q&A area, we can get to those. So while we are waiting for some questions to come through, I did have a question. So a lot of these examples, they were binary. So is it possible to add in other other options?
Yes. So essentially what would happen is you would, the lingo gets kind of wonky, but essentially what would happen is now you would expand that those columns. So how I said there were only two outcomes, true or false, yes or no. And then that affects how many rows you have, true or false, yes or no. You would then expand your column. So you would have, yes, no, and then some secret third thing on both the next column and the next row. And then you would go through and match your guesses to where they need to go. So if you predicted 2 when it should have been 3, then there will be now a new box in the grid for you. So the confusion matrix grows and gets only more confusing.
Yeah, it sounds like it. So would those formulas change at all with those added columns?
They would expand, but the gist of the formula would not. So it would still only work across rows and columns and things like that, but it would be different. It would look different if I wrote it out as a formula, but if you saw it on the matrix, you'd say, all right, I see exactly how this is expanded.
Awesome. Yeah, it does sound like it will get a little more confusing, but you are very clear in your delivery, and I feel like we definitely cleared up the air on this topic. All right, so we'll just leave a few more moments for people to chime in for any additional questions.
Sounds good to me. And if you don't want to ask, obviously, if you don't want to ask the questions like, out and about like this, then as always, feel free to reach out to me on any of these channels or via Measure Slack. I'm also decently active on Measure Slack. So if you'd like to just ask any questions one-on-one, then I definitely have the time to answer those as well.
Perfect. Yep, and just like Jamarius said, we'll be sharing out these slides as well as the recording, so you can watch it back, pause it, try it on your own, and Jamarius will be there to answer your questions. So, all right, it looks like that is all for today. So thank you so much, Jamarius, for teaching us today. I definitely learned a little bit more about the confusion matrix. So thanks for everybody joining today, and we'll see you at our next SDEC session.
All right, see you folks.